Hello and welcome to this presentation from the Igshpa 2017 venue in Denver, Colorado. The presenters will be Gregory Turon, Senior Application Engineer, and Adam Dahlquist, Business Development Manager at SWEP North America. The presentation will focus on key developments to counter freezing and fouling in brazed plate heat exchangers in reversible systems.
Main objectives of our presentation are to describe the latest development on BPHE technology as well as system solution to counter freezing and fouling. If we go one step deeper, we are going to introduce you how to evaluate the freezing behavior and how to define the freezing boundary of a brazed plate heat exchanger. Also, we will review the latest development in BPHE technology and potential system implementation to counter risk of freezing and fouling.
Trends in the heat pump industry. The most commonly used refrigerant in heat pumps is 410A. It does have a high global warming potential, so there is a lot of refrigerants that wants to take its place, but there is no clear roadmap how and when this can happen. So we see that 410A will remain with us. However, there is a strong trend to lower the refrigerant charge in systems, reaching a higher BTU per pound of refrigerant, and the reasons also being economic, as you can save money on refrigerant doing so. There was more than 170 countries that met in Kigali in 2016 to cap the refrigerant usage in 2019 and start phasing out in 2024. This is not yet law, but if it becomes, it will have a strong impact on the trend of lowering refrigerant charge. The efficiency. The energy prices have been very volatile the last 10 years, from very high to very low to average about now. Regardless of the energy price, to have an energy efficient heating solution is always a good thing, so you don't have to worry about the energy price. And the incentives, they are now gone. The Energy Star incentives are gone. So the main economic driving force left is the payback, which is the installation cost of a ground source compared to alternative technologies, and the perceivable operational savings that you can get from that heat pump. So what can a component manufacturer like SWEP do to improve the payback situation for the end customer? Well, going from the most commonly used heat exchanger technology today, the coaxial heat exchanger, to the brazed plate heat exchanger, and even more so the asymmetric brazed plate heat exchanger, will allow that the heat pump system becomes high performing with a higher EER and COP, at least 10% better. It will have the heat exchanger has a smaller physical size, allowing for a smaller system solution, making it easier to assemble, to transport, to get installed into the final location. Less weight, again, easier to assemble, easier to transport and to install. And a drastically reduced refrigerant holdup volume, leading to less refrigerant, less GVP, and also less cost for refrigerant. Why aren't all heat pumps in the US equipped with a brazed plate heat exchanger? Well, for SWEP to be able to let our heat exchangers make the full benefit for the end customer, we have to go through our customer, the ground source heat pump manufacturer. And surprise, surprise, the heat pump manufacturer have other things on his mind than what heat exchanger technology to use. He's looking at what's the efficiency for this heat pump, where we want to go with that, how is the market changing, what is competition doing, what kind of refrigerants are we going to use. And then there is the fouling and freezing challenge. And the fear of fouling and freezing, SWEP have noticed, is the most common reason why a heat pump manufacturer do not use a brazed plate heat exchanger and instead the less efficient and heavier coaxial heat exchanger. So SWEP has wanted to attack fear with facts.
If we take one step back and look on the heat pump market globally, we can divide it into two kinds of markets. The first one, it's what we consider as a mature market, like in Europe or to some extent in Asia. In these markets, BPHE is the standard heat exchanger technology, but due to market change, system manufacturers have to extend the envelope of their product without doing any compromise in terms of system reliability. Due to this new market requirement, BPHE freezing and fouling behavior is getting more and more noticeable. Second kind of market is non-penetrate market, like North American heat pump, for example. System manufacturers are used to other heat exchanger technology as a standard, and as already explained by Adam, a fear or concern exists about freezing and fouling in regards to BPHE technology. So, in order to support the integration of SWEP brazed plate heat exchanger into our customer systems, for all kind of market, we decided to initiate a freezing and fouling project. Based on market needs and expectation, we have defined following main objectives for project. First, provide anti-fouling and anti-freezing guideline on a component as on a system level. Second, establish clearly the BPHE freezing and fouling boundary. Also, we want to use the knowledge gained over our project in order to develop BPHE which are more freeze resilient and less foul sensitive. Last but not least, we want to develop proactive and reactive solution in order to overcome those challenges. First, we will review our freezing project, but before to go through all details, I would like to introduce you the theory behind it. Let's consider an heat exchanger, any kind of heat exchanger. In one side you have pure water, on the other side of the heat transfer area you have an evaporating temperature about 35 degrees Fahrenheit. Is it a risk of freezing? For sure, no. But now if we consider similar case with an evaporating temperature about 25 degrees Fahrenheit, that makes it a bit more tricky. It's difficult to say if it's a risk of freezing or not, because what is important in order to evaluate freezing risk is the wall temperature or surface temperature, which you can see on this slide. And the wall temperature or surface temperature, it's a function of the evaporating temperature, film coefficient on refrigerant side, film coefficient on water side, and the water temperature as well. We tried to simplify it a little bit, and we end up with a function which can evaluate the wall temperature based on the water temperature, refrigerant temperature, and the mass flow ratio. The mass flow ratio is the ratio of the water flow to the refrigerant flow. Why is it the mass flow ratio an important parameter? Let's consider what's happened if you change the mass flow ratio. In fact, if you increase the mass flow ratio, which means if you increase the water flow for a constant refrigerant flow, then the surface temperature or wall temperature will get closer to the water temperature. On the opposite, if you decrease the mass flow ratio, then the surface temperature will move towards the evaporating temperature. So, as a conclusion, in order to evaluate the risk of freezing for a brazed plate heat exchanger, what is important to consider is the water temperature, the evaporating temperature, the mass flow ratio, but also the heat exchanger design or the brazed plate heat exchanger design, as it might change the film coefficient on either side of the heat transfer surface. The wall temperature or surface temperature is a good parameter in order to evaluate risk of freezing. But unfortunately we can't measure it continuously and all over the heat exchanger. So we developed a method in order to be able to define the freezing temperature of a brazed plate heat exchanger at specific condition. By combining the test result of a couple of test points, we are able to develop this three-dimensional graph where in one axis you can see the water temperature, on the second one you have the mass flow ratio, and on the third axis you have the minimal evaporating temperature. Based on this graph, we are able to predict what is the minimal evaporating temperature for a specific heat exchanger under any possible condition. Also, this three-dimensional graph gives you an indication about what is the effect if you lower the water temperature. And then, for example, you can see the minimal evaporating temperature, it's higher for a low water temperature than for a high water temperature. You can also see what is the effect if you lower the water flow for a constant refrigerant flow. And one additional comment, which I think it's quite interesting, it's normally when I'm discussing with people about what are the expectations in terms of minimal evaporating temperature. Normally their expectation is much higher than what you can see on this graph. For example, on this graph you can see minimal evaporating temperature about 10 to 23 degrees Fahrenheit, which is quite low. If you remember the introduction of a project, main objectives are to define BPHE freezing boundary, but also to develop heat exchangers which are more freeze resilient. So how can we improve the freezing resilience? For that, one of our activities is to run CFD simulation between various designs. On this slide you have an example, a comparison between two designs. We are looking around the refrigerant inlet port and on the water channel. What is interesting to evaluate is the homogeneity of the water flow. And what can we see on this slide? For design A, we can see some red areas here on the top, which mean much higher water flow in comparison with the mean value, but we can also see some light blue and dark blue area, which indicate a much lower water flow. For design B, even if we have some spots on the top of this picture with a slightly higher water flow, we can see an homogeneous water flow. If you don't have a long experience with CFD simulation and BPHE freezing behavior, which I guess is your case, it might be difficult for you to say which design is better than the other based on CFD simulation. But with this graph, I will try to make it a little bit easier for you. What you can see here is a comparison between the three-dimensional graph of a product using design A and a product using design B. So, which design will you select, or which option will you select? It's maybe still tricky for you to say, but what we can see on this graph is design A has a lower minimal evaporating temperature for application with high water temperature and high mass flow ratio, which are operating conditions where it's almost no risk of freezing. For design B, we can see a more stable minimal evaporating temperature, and we can also see a lower minimal evaporating temperature for application with low water temperature and low mass flow ratio. As we will see it later on, application with low mass flow ratio and low water temperature, it's what we can consider as the worst case for a heat pump application. So, based on this graph, we can conclude on design B as being the most suitable option for heat pump application. So far, we have been discussing about how we evaluate and define the freezing boundary of a specific heat exchanger. Also about how we can compare BPHE design between them, but for you, I think what is the most interesting is to understand how you can use it into your system. For that, I would like to share with you an example from a cooperation with one of our European heat pump customers. On this slide, we will focus on gray area, which are when they run the defrost cycle. During other period of time, the brazed plate heat exchanger is used as a condenser, so there is no risk of freezing. What we did was to evaluate the possibility to use a polynomial function extracted from our 3D graph as a freeze protection. For that, we compared it with another method, which is what we call visual freeze detection. The visual freeze detection method is the two pictures which you can see on the top part of this slide. If you look on the first defrost cycle, the dark spot inside the red circle is a visual freezing indication. Now, if we compare at the bottom of this slide, the evaporating temperature curve, which is in blue, with SWEP recommended minimal evaporating temperature in red, what we can see is for the first defrost cycle, the evaporating temperature is getting below SWEP recommendation. And also we were able to detect a visual freeze indication. For the second defrost cycle, the evaporating temperature gets close to SWEP recommendation, but never below it. Also, we haven't been able to find any visual freezing indication for this cycle. So, after some additional qualification tests, our customer has decided to implement SWEP recommended minimal evaporating temperature into their control strategy. And now, based on it, they are able to counteract on cases where the evaporating temperature gets close to the freezing boundary of the system. For fouling as for freezing, I think it's important to understand the theory behind it. From your point of view, is it a risk of fouling for application with clean and soft water? For sure, no, but unfortunately it doesn't exist in our industry. So one of the most critical parameters in order to evaluate risk of fouling for an heat exchanger is the level of turbulences inside the heat exchanger. Higher is the level of turbulences, lower is the risk of fouling due to self-cleaning effect. But is it any difference between heat exchanger technology? Yes, of course, otherwise it would have been too easy. The main difference between a tube-in-tube heat exchanger or a shell-in-tube heat exchanger and a brazed plate heat exchanger is the level of turbulences at which you will reach a turbulent flow. A tube-in-tube heat exchanger or a shell-in-tube heat exchanger require a Reynolds number about 2000 or above 2000 in order to enter into turbulent flow regime. When a brazed plate heat exchanger will enter turbulent flow regime for Reynolds number above 150. What does it mean? In fact, if you take two heat exchangers, for example a tube-in-tube and a brazed plate heat exchanger, with similar water quality, similar water flow and hydraulic diameter, the brazed plate heat exchanger will have a higher level of turbulences, which then will lower the risk of fouling. But now, if you want to clearly understand what is the fouling sensitivity of a specific heat exchanger, what you must consider is the water quality, the water temperature, as above certain temperature scaling may happen, the Reynolds number or the shear stress value, as it's a good indication about the level of turbulences. And as for freezing, we must consider the BPHE design, as the design might change the level of turbulences and the water flow distribution. How do we evaluate the fouling behavior of an heat exchanger? For that, we built a test rig in our lab where we can compare different heat exchanger design under various water flow, water quality, and water temperature. Based on our test result, we are already able to draw some clear conclusion and to boil it down to recommendation. One of them is a recommendation about minimal shear stress value for various water flow quality. Worst is the water quality, higher must be the shear stress value. As a conclusion for projects, as indicated, we have been able and we are evaluating BPHE sensitivity and resilience through SWEP freezing and fouling test. From our test, we can now clearly define the comfort zone of SWEP brazed plate heat exchanger in regards to freezing based on the water temperature, evaporating temperature, and mass flow ratio. Also, we defined guidelines about minimal shear stress value for various water quality in order to minimize the risk of fouling. Based on that, we have been able to improve the design of our BPHE in order to make them more freeze resilient and less foul sensitive. As already explained, different BPHE design result in different operating envelope. Also, we distillate all this valuable information into a SWEP engineering guideline for reversible heat pump application, and we have used it in order to develop some proactive and reactive solution. And now I would like to let Adam introduce you some of our project outcomes.
So on the previous slide, you saw what kind of scientific data did we get out of the project, and I would like to go through what kind of commercial outcome we got from this project. What we learned was from how the heat exchanger is freezing, what kind of the parameters. We saw what asymmetry can do, and we also learned how to improve the design of the plate to make it more efficient and less prone for freezing. SWEP has over 35 different brazed plate heat exchanger models. For reversible heat pumps, we have now a complete range from less than 1 ton up to more than 30 ton of reversible duty, with the 8 LAS, 26 ADAS, etc. Some of them are symmetric, some of them are asymmetric, depending on what is the requirements of the application. We have single circuit with one refrigerant circuit and one water circuit. We have dual circuits with 2 refrigerants and 1 water circuit with using different refrigerant systems. We are using the asymmetric design, lowering the water pressure drop. We have optimized the chevron angles and design of the plate based on what we have seen with the CFD and the freezing test. We are working with several different types of evaporator solutions, distribution solutions that assure that the refrigerant is going into the right channels. And all of these units here have been freeze and fouling tested so that we are able to help you with the operating envelope to avoid freezing. Another project outcome was the cooperation between SWEP and the flow specialist company SIKA. What SWEP have seen is that the most common reason for freezing in a reversible system is that there is no water flowing on the water side. So if the water is not flowing on the water side for any reason, it could be that the pump stopped working, that the valve shut, or by human mistake, and the compressor is still running, the water temperature will of course go down and freezing will happen relatively fast. Not all heat pumps in US are being equipped with the flow sensor to avoid this. A flow switch being the most cost-efficient solution, but many are. And what we've seen is that the flow switch being used for this is typically one size fits all. So the same flow switch is used for a 1-ton and a 6-ton machine, and that's better than nothing. However, if you're using the same flow switch also for a big capacity machine, you will be able to reach a very low mass flow before the flow switch stops the compressor. So what SWEP and SIKA did in a cooperation was that SWEP defined the flow levels that we thought were adequate for turbulent flow and not to limit the operating envelope of the system. And SIKA developed a flow switch range that are color coded for the different capacities between 2 and 6 tons. So that means that for each tonnage of heat pump, it's possible to find the SIKA flow switch that will stop the compressor if the ratio goes below about 4.5, which is about half the nominal flow of 3 GPM per ton, which is the industry standard flow range. And by using this flow switch, number one, you have the protection against pump failure, and number two, you have you know that you're operating inside a very safe envelope of the heat exchanger where freezing is very unlikely to happen.
Thank you very much for attending this technical presentation. We remain at your disposal for any potential cooperation. If you may have a question, don't hesitate to contact your SWEP representative or to drop us an email at following address. Thanks again and goodbye.